Good morning, students. And last time you have learned the kinetic derivation of first order reaction. Let us revise once again. Here, all of you know the first order reactions are the reactions in which a rate of reaction it depends on the concentration of a single reactant. Okay, the rate of reaction it depends on the concentration of a single reactant. That means there involves only one reactant, or if there are two or three reactants, still the rate of that reaction it depends only one reactant's concentration. Such reactions are called as first order reaction. And here in general, we consider a first order reaction as our A, it is our reactant. Here A, it is our reactant. See here, A, it is our reactant and it gives product. This is our chemical reaction. And if we consider Ca is the concentration of reactant A at any time T, then the rate of the reaction we can write as minus dCA by dt. That means a rate of change of concentration with time, and it is proportional to concentration of reactant, that is the Ca. Or we can write this equation as minus dCA by dt, it is equal to K into Ca, where this K is the proportionality constant and we call this K as rate constant or velocity constant or specific reaction rate. Last time you have learned this. Okay, then if we consider this small a as the initial concentration of the reactant A and X is the decrease in concentration in time t, then the concentration remaining at time t, it is the A minus X. You know, this A, it is the initial concentration. That is, we have the concentration of A, it is equal to A minus X at time t. Therefore, we can write this value of Ca in this above equation. We get minus d in a bracket A minus x upon dt. It is equal to K into bracket A minus x. And rearranging this equation as we put this term of right hand side towards left and left hand side term this dt towards right hand term. Here we get dx by dt, it is equal to k in bracket a minus x. Okay, we get here dx upon a minus x, it is equal to k into dt. And integrating this above equation, here integration of dx upon a minus x, it is equal to integration of k into dt. Remember, the integration of dx upon a minus x, it is the minus log a minus x. It is equal to kt plus c, where c is the constant of integration. And to find the value of c, if we put t it is equal to 0, that means when time t it is equal to 0, the decrease in concentration x it is equal to 0. In the above equation, we get minus log a, it is equal to c. Then putting the value of c here, we have equation minus log a minus x, it is equal to kt plus here minus log a. The value of c here it is the minus log a. Then we transfer this term minus log a towards left hand side and we rewrite the above equation. Therefore, we have log of a minus log of a minus x, it is equal to kt, or log of a upon a minus x, it is equal to kt, where this log with base E. And to change this log to the base E, we can write here K it is equal to 2.303 upon T into log to the base 10 A upon A minus X. And this is the kinetic equation of the first order reaction. Okay, and in this equation, K it is the velocity constant or rate constant, T it is the time, and A it is the initial concentration. This A minus X it is the decrease in concentration in time T. Okay, this equation is the first order kinetic equation. Okay, then our next point, it is the characteristics of first order reaction. There are number of characteristics of first order reactions, and for your syllabus there are only 6 characteristics. So study well that 6 characteristics. Let us see one by one the characteristics of first order reaction. See here, characteristics of first order reaction. The first characteristic is the time required to complete a definite fraction of the reaction. Time taken to complete a definite fraction of the reaction or half-life time is independent of the initial concentration of reactant. I repeat, the characteristic of first order reaction, and the first characteristic, the time required to complete a definite fraction of the reaction or half-life time is independent of the initial concentration of reactant. And this is shown by putting here T as T1 half and decrease in concentration, that means X it is equal to A by 2 in the first order kinetic equation. Here the velocity constant of first order reaction, it is given by K it is equal to 2.303 upon T into log to the base 10 A upon A minus X. And in this equation, when we put this T as T1 half and this X as A by 2, that means half reduction. Okay, here we put X as a by 2, then we get this K it is equal to 2.303 upon T 1 half into log to the base 10 A upon A minus this X we have put as A by 2, and here we get T1 half it is equal to 2.303 upon K into log to the base 10 A upon A by 2. Here A minus A by 2 it is equal to A by 2. Okay, and here this A divided by A by 2, that means we get here log 2, and the equation we have as T1 half it is equal to 2.303 upon K into log 2, and all of you know the value of log 2 it is the 0.3010, and here the product of 2.303 into log 2 it is the 0.3010. The product of this we get 0.693. Okay, the product of these two values it gives 0.693 divided by K, and this is the equation for T1 half or half lifetime, it is equal to 0.693 divided by K, and as this equation it does not contain any concentration term. Okay, any concentration term here. So we can say that the half-life time or time taken to complete any fraction of reaction is independent on the initial concentration. And by using this formula, we can calculate either the value of K or either the value of T1 half or time taken to complete any fraction of the reaction. And this is the first characteristic. Then here the second characteristic, the velocity constant K depends on the units of time and is expressed in a reciprocal time inverse. Okay, a reciprocal time units. And last time you have learned this. Here, if the time t is given in a seconds, or if we express the time t in seconds, we have the unit of k as second inverse. If we express the time of a reaction in terms of minutes, then k is expressed in minute inverse. Or if we express the time in hours, then the k has unit as a hours inverse. Okay, here the velocity constant k depends on the units of time and it is expressed in a reciprocal time units. Remember, this is the second characteristic. Then the third characteristic, velocity constant k is independent on the units used to express the concentration. Remember, the velocity constant k is independent on the units used to express the concentration. Here we have the equation for velocity constant as follows. Here we have k, it is equal to 2.303 upon t into log a upon a minus x. This is the formula for velocity constant of the first order reaction. If we express the concentration in terms of mole per dm cube, that means in this term we have two concentration terms, numerator concentration term and denominator concentration term. And these two concentration terms, they cancel each other and the unit for K, it is the time inverse. So here we have expressed the time in seconds. Therefore, we get the velocity constant has a dimensions as second inverse. Okay, and this shows that the velocity constant k is independent of the units used to express the concentrations. Okay, this is the third characteristic. Then the next characteristics here, see here, the velocity constant k depends on the temperature. Okay, the velocity constant k depends on the temperature. As we increase the temperature of the reaction, the velocity constant of that reaction, it also increases. Remember, then the next characteristic, all the reactions of first order satisfy the equation, and that equation all of you know. Here k, it is equal to 2.303 divided by t into log a upon a minus x. Okay, all first order reactions, they obeys the this equation. And in this equation, all of you know, this A, it is the initial concentration, and this A minus X, it is the decrease in concentration at time t. Okay, and putting the various values of A and A minus X and time, we can calculate the different values of K. And remember that In case of first order reaction, all the velocity constant k have the same values or constant values. Then see here the next characteristic, here it is the graphical conformation. Okay, the next characteristic and important characteristic, here it is the graphical conformation. Here all of you know we have the first order reaction equation as K, it is equal to 2.303 upon T into log A upon A minus X, and when there is a no base here, assume that there is always base 10. Okay, so we rearrange this equation as log of A upon A minus X, it is equal to K into T upon 2.303, and when we plot the graph of log of A upon A minus X versus time t, we get a straight line passing through origin, and it indicates this is the first order reaction. And the value of slope, here it is slope, it is equal to k upon 2.303. The value of slope, it is equal to k upon 2.303. Thus k, it is equal to 2.303 into slope. By using this equation, okay, we can find the value of k when we plot the graph of log of a upon a minus x versus time. Okay, then again the above equation can be written as this equation, this one here, log of a minus log of a minus x, it is equal to k into t upon 2.303, and we can write this as this equation as log of a minus x, it is equal to minus k into t upon 2.303, and we put this term here, so it becomes plus. Okay, therefore we have the log of a minus x, it is equal to minus k into t upon 2.303 plus log a, and if we plot the graph of log of a minus x versus time, it gives intercept on y-axis. Here again we obtain a straight line with intercept on y-axis. Okay, and the value of intercept, here it is log a, and the slope, it is equal to minus k upon 2.303, and here the from this equation we can calculate k as k, it is equal to minus 2.303 into slope. These are the characteristics of first order reaction. Okay, and study well. Depending on this graphical representation, you have to perform one experiment. I will provide you the readings of the hydrolysis of methyl acetate in presence of HCl next time, and you have to plot the graph of here log of a upon a minus x versus t. Remember the nature of the graph, it is the straight line passing through origin, and the value of slope, it is equal to k upon 2.303, and we can find k value as k, it is equal to 2.303 into slope. And see the second graph here, log of a minus x upon t, this is the again straight line with intercept on y-axis, and the value of intercept, it is equal to log a, and slope, it is equal to minus k upon 2.303, and k, it is equal to minus 2.303 into slope. Okay, these are the characteristics, and the next point here it is examples of first order reaction. Again there are many examples of first order reaction, but here I will explain you few examples of first order reaction. See here, the decomposition of H2O2. Decomposition of H2O2, hydrogen peroxide, it decomposes into water and oxygen, and the rate of this reaction, it depends on the concentration of hydrogen peroxide. So it is a first order reaction. Then the another example, decomposition of N2O5. Here, after decomposition of N2O5, we get 4NO2 plus O2, and the rate of this reaction, it depends only on the concentration of N2O5. Again, the decomposition of oxalic acid, and in the decomposition of oxalic acid, we get uh, carbon monoxide, carbon dioxide, and H2O. It is the example given in your book. Then the conversion of cyclopropane into propane. It is also a first order reaction. Then the another example here, ethyl methyl ester and water. That means hydrolysis of ester. It produces acid and alcohol. Here we have the acetic acid and ethyl alcohol, and the rate of this reaction, it depends on the concentration of ester. Okay, then the inversion of cane sugar, we get glucose and fructose. Okay, then the pseudo first order reactions, that means false first order reactions. Here, such reactions in which the molar concentration of a reactant remains practically unchanged and small change in concentration does not affect the rate of reaction are called pseudo first order reactions. And for example, the hydrolysis of sucrose, here we get glucose and fructose, then hydrolysis of ester, either methyl ethyl ester or okay, these hydrolysis of ester and hydrolysis of sucrose, these are the examples of pseudo first order reactions. And pseudo first order reactions means here there are two reactants, okay, sucrose and water, here ester and water, but the concentration of water, it is in a excess, it does not interfere the rate of reaction. Okay, and the rate depends on the concentration of sucrose here and ester here. Such reactions are called as pseudo unimolecular reactions. Okay, and all of you know the rate of reaction, it is given by minus dA by dt, it is equal to K into concentration of A. We have seen this, and next time you will learn the second order reactions. Thank you.